So, welcome. So, first law of thermodynamics. We've got 3 more bits to do. First law of thermodynamics, then we do some statistical mechanics, some Boltzmann's type stuff, and then we do heat engines. First law of thermodynamics deals with a lot of stuff that I think you might have seen if you've done chemistry before, or maybe in high school. We're going to deal with basically the distinction between heat and internal energy. We're going to talk about calorimetry. We'll talk about the first law of thermodynamics itself, and we'll talk about heat transfer mechanisms. So there's a fair few bits in here. And what you notice is that towards the end of the course, a lot depends on knowing equations. We don't go very deep into any equation. It's almost like, oh, I see that, I know that. And, I can change the geometry on you, I can change the units on you, but there's not a tremendous amount I can do at this point. We need a few more definitions. So internal energy is the thermal energy inside the object. I can change its mechanical energy by just moving it in a gravitational field. Agreed? That's not changing its internal energy. Its internal energy is its energy reference to itself. So lifting it doesn't change its internal energy. If I lift it and drop it, then maybe I can transfer some of that mechanical energy into thermal energy. That's a different mechanism. Just moving it to give it more mechanical energy does not change its internal energy. So I have if you like, the external energy, which is the kinetic energy, the potential energy of the thing as a whole, and then I have the internal energy. Now, there is motion of the particles, so there is this internal kinetic energy, and I sometimes squish things together, so there is some internal potential energy, but it's distinct from the actual gross mechanical energy of the system. It doesn't get hotter just because I throw it. You know, it gets hotter if it hits something and lands, but not just because I throw it. So internal energy, you take all the little vibrational energies and the electrostatic energies and you add them together, and that's your internal energy. That is like your bank account. Think of that as your bank account. You have your internal energy, sometimes called your thermal energy, and think of that as like your bank account. And it turns out there's 2 ways to get energy into and out of the system. I can put a Bunsen burner underneath it, or I can put ice around it, and that is putting energy in or taking energy out by heat. And I can scrape it along the walls. I can rub it, I can hit it. I suppose I could expand it if it was a gas. And that is doing work on or having it do work on. So you can put energy in and out through work. If you expand it, you take energy away. If you squish it, you put energy in. And this is, I think of this as been very much like the ATM and you know what the teller is? The teller is the person inside. You tell them what you want. Person behind the counter, and you say, I want to draw out $100, I want to put in $100. 2 ways into and out of your bank account. Supposing I was like shocked, and I said, but I don't understand. I put $100 in my bank account. You were with me. You came with me. You saw me putting $100 in my bank account. You came inside and stood next to me when I paid that $100 over the counter to the lady. But now I look and I see that there's $1,000 taken out of my bank account. I just can't imagine how this would have happened. What's the devious possibility? Let's say that I'm not the most honest person in the world. What do you think I probably did that caused, although I put $100 in across the counter when I went to see the teller, what did I do to take out overall $1,000 in my bank account? What did I do? I went to the ATM, didn't I? And you said, well, look, you went to the ATM. I know. You took $1,100 out of the ATM. You put 100 in, ooh. Then you take $1,100 out, and oh, lo and behold, you've lost $1,000. You didn't lose it, you took it out. Come on. Well, that seems, a bit devious, but you know how it goes. In chemistry, so what they'll do is they'll say, oh, I don't get this. I put a Bunsen burner under my cylinder of gas, and yet it's lost energy. How can this be? How can you have the temperature going down the gas when you put a Bunsen burner under it? Because Bunsen burners make things hotter. They never make things colder. And all that happened was you expanded the gas more than a lot. And expanding caused cooling, and heating caused warming. And if you do more expansion and less heating, you cool the gas. Even though the Bunsen burner is still there. It's no great mystery. As long as you're familiar with, you can do that. So I remember thinking, I didn't get that for the longest time. I couldn't visualize it. It was just like an equation. We've got to shove the numbers in. And I kept putting the numbers in with the wrong signs. And oh man, it was a pain. And then finally I realized, it's just like a bank account. You have your ATM and you have your teller, you have your heat and you have your work, and you can do things with either one of them. And the game they like to play is they say this change happens there and this change happens there, so what happens here? It's only three things you're playing with. There is a little bit of a confusion, which is how we define work. Because there's not unanimity. People disagree in different areas. We'll get to that. So internal energy is all the energy of the system that is associated with its atoms and molecules. When viewed from the reference frame at rest with respect to the object, a sample's temperature is directly related to its internal energy. So think of, so that's a subtle but important point. So I have this thing called internal energy, sometimes called, E, sometimes called thermal energy. I have this thing called internal energy, and what I can tell you is if I have a body of anything and I increase its E, I increase its temperature. And if I decrease its E, I decrease its temperature. And there's no way around that. So the temperature is like a telltale for what your internal energy is doing. It's kind of telling you, it went up or it went down. It's not equal to the change, though. So I'll give you two examples. My wife is the kind of person who puts 90% of her salary into her savings account and 10% into her checking account. And I'm completely the opposite. I'll put 90% of my salary into my checking account and only 10% into my savings account. And the problem is if you only use one or other of those accounts as the telltale. If you say, well, look, we'll just look at people's savings accounts to see how much they really have in terms of wealth. We don't care about checking. We'll just look at savings account. Then you'll see my wife is very wealthy because she puts a lot of her salary into her savings account. And I'll appear not so wealthy because I'm only putting 10% into my savings account. And that's the problem we have with temperature. Temperature does not reflect all of the internal energy. It reflects part of the internal energy. And some materials store most of their internal energy in the part that affects temperature, the vibrational part. And other materials put proportionately little of their internal energy into those bits. So when you put energy into something, some materials get hot really quickly and other ones don't. They get hot, but not so quickly. The key thing is, as their internal energy goes up, the temperature does go up for both of them. It just goes up at a different rate. So temperature is a telltale for how your internal energy is changing. When temperature goes up, your internal energy is going up. When temperature goes down, your internal energy is going down. But it's not equal to it. So there's this we've got to take that into account. And that's specific heat and all that kind of stuff. So heat is the transfer of energy across the boundary of the system due to temperature difference. So Bunsen burner's hot, your test tubes cold, etc. Work is the transfer of energy across the boundary of a system due to its mechanical energy. You know, we can just get heat, basically, we can just by doing that. So, the SI unit for heat is the joule. Good old Joule, on his honeymoon actually, him and his wife were up in the Alps measuring the water temperature at the top of a waterfall and the water temperature on the bottom of a waterfall, and basically getting to the stage where convincing himself and then convincing the rest of the world that this idea of the caloric fluid that thermodynamics had been based on before was really just a misnomer. It's just the same kind of energy that we have mechanically. It's just an internal energy as opposed to an external energy. So why not just call it by the same unit? So we call the internal energy joule rather than calorie, which is what we did before. And heat is going to be called by joule because it's the transfer of energy. A traditional unit for heat is the little calorie, which is the amount of heat needed to raise the temperature of 1 gram of water from, why not 0 to 1? Well, you've got to pick a number. So they said 14.5 to 15.5 degrees C, about room temperature. A little bit of a cool room temperature, but about room temperature. The energy content of food is often measured in big calories, big C calories, which in Europe they call the kilocalorie. They don't mess about in Europe. It's like a kilocalorie, so you know, oh, it's 1,000 of the little calories. Some industries measure heat in British thermal units, which is the amount of energy required to raise, I think it's 1 pound of water by 1 degree F. So kicking around today, we have the big calorie, we have the little calorie, we have the BTU, and of course we have the joule. And it's nice to be able to do conversions between them. Which unit is smallest? So I'm giving you some conversions here. Let's see if we can figure, is there a common thing here? So little calorie, little calorie, little calorie. So we'll do this. So if we have the calorie scale, so we have 1, I'm going to call it the food calorie. This is 1,000 little calories. So that's not a very small unit. A BTU, one BTU. I think I did that right. Yeah, I did that right. And then, oh man. 1 joule. 1 joule is less than 1. This is 1 calorie. So if I went in order, the joule would be the smallest, then I'd have the calorie, then I'd have the BTU, then I'd have the food calorie. Isn't that amazing? The food calorie is by far the biggest unit of energy, thermal energy that we use. It's huge. So which is the smallest unit would be the joule. Yeah. You don't need to know those numbers. It's like, factor label method. We've not done that for a while. So using the factor label method, convert 17 BTUs into joules. So I need some conversion things. I can go from BTU to calories and then from calories into joules. So that will work. So we have BTU goes on the bottom. Do you remember how this goes? Calorie. 1 BTU is 252 calories. BTU goes away. And then I want to get rid of calories. And I have joules. 1 calorie is 4.186. And so we just multiply this out and we get 17 times 252 times 4.186 divided by 1 divided by 1, doesn't matter. And we're going to get 17933 joules. This is a great opportunity for me to just reach back and say, do you remember how to do your factor label? I see occasionally people doing conversions, and I'm a bit saddened when they don't use factor label and get it wrong. if you don't use it and get it right, you're better than I am. But if you don't do it and get it wrong, then the reason why I use it is because it works. If I do it in my head, I'll get confused. So this is. Let's look at this question because it's kind of interesting. So this is actually it came out of so I met my wife when I was 45, and you're gonna go in. People go in plateaus. You can tell a teenager from a young adult, from an adult. There's this plateau from about 18, for most people, 17, 18 to about 28, and they kind of like they're pretty standard. They'll look the way they are. They're about as fit as they are, etc. Then late 20s, early 30s, there's another plateau, and it goes on until your mid-40s, really. You can tell a 30-year-old from a young 40, it's a bit hard, but a mid-40, you can tell, it's kind of there's this another step. And then 40s, mid-40s up until I think about 60s, you can tell, and then 60s, you're on this another plateau. And these changes happen quite quickly. My experience is, suddenly I just was like, everything had changed. It was like, whoa. And suddenly, just, so anyway, I think that I got married to my wife right before I went through one of these changes because, I look at pictures of before we were married and I was quite fit. And then within a few years of us being married, I look older. And she said to me, I remember we'd been married a few years, and she said, I noticed you're kind of like putting on a bit of weight there, Tony. And I said, it's cooking. Remember for like 45 years, I had to live off my cooking, and it was awful. And now I get to live off your cooking, and it's great, and all that. And she said, well, it'd be really good if you kind of like got a bit fitter. I said, I got it all taken care of. I said, because I don't know if you've noticed, but, we both worked at USF, so we'd meet for lunch. So I said, I don't know if you've noticed. And she worked on the 4th floor of a building, So I said, I've stopped taking the elevator. So now when I come to see you, I climb the stairs, It's going to do it. And my wife's really smart. And she goes, let's do the math. So let's do the math. Because I also have I've always had a sweet tooth. And I'm one of these people where I run out of energy in the afternoon, and traditionally I'd go to the machine, and I remember I would get a Snickers bar, I would get some Skittles, and I'd usually get something else. I'd get like 3 candies and just eat them, and then I'd be good to go for a long time. And I never thought anything of it. And then some of my colleagues, remember my old boss's boss saw me doing this. And he said, man, you are going to be, you got to stop that. And I just never, I thought everybody did it. And apparently everybody doesn't do it. So I had this, she'd find Snickers bars in my, wrappers in my pocket. And so she said, let's do this calculation. And it's kind of frightening, really. So show that an 80-kilogram teacher, that was me, would have to climb that high to work off that number of calories that are in a Snickers bar, okay? So we go, well, the energy, we're saying the energy in candy is going to be equal to the work done, yeah? And the energy in the candy is 250, let's move that over, 250 food calories. Well, I want little calories, so put the big calories underneath and the little calories on top, and one big calorie is 1,000 little calories. And then I want to go from little calories to joules. And so J-O-U. And so we find that, what did we say? 4.8, was it? 4.186 is equal to 1 calorie. So that's going to be equal to, and that altogether is going to be equal to, well, the force, which is my weight, which is 80 times 10 times how high I climb. Yeah? That's the equilibrium. So I'm going to say 250 times 1,000 times 4.186 is equal to 1046500. Now, we don't usually put commas in, but that's over 1,000,000 joules. A Snickers bar is over 1,000,000 joules. What's my visualization of a joule in mechanics? If I want to visualize a Newton, what do I visualize? Holding an apple. And what's my visualization for a joule? I pick the apple up from where? From the floor. And where do I put it? How high do I lift it? A joule is 1 Newton per meter. 1 Newton meter, I'm sorry. So you pick it up and put it on the table. If you want to visualize a joule, imagine picking an apple up and putting it on the table. When you eat a Snickers bar, it's like doing that 1,000,000 times. It's a frightening amount of energy. And that equals 800H. So H is going to equal that divided by 800, which equals 1308.125 meters. A meter is like 3 feet. So this is like, let's just time it by 3. That's like 3924 feet, approximately. If you take, how high is this ceiling? This ceiling is probably what? You think it's like, yeah, where's 5 or 6? I'd say 10. 10? 10 or 12, actually. Let's say 10. That would be 390 approximately floors. I mean, how many buildings do we know are 390 floors tall? I mean, it's like a huge amount. So me climbing 4 stories to get to my wife's office is going to burn off the tiniest amount of a Snickers bar. If they put on the Snickers bar 1,000,000 joules, even I'd pause before I ate it, you know. But it's 250. That's 250. It's fine. There was something I wanted to tell you, and it was no. I think it's fine. Work. Yeah, I think that's fine. We're up to speed. Okay. So now we start trying to put these things together. We're going to isolate a system. Oh, hold on 1 second. Why do we do this? We've been going for an hour. Let's just put this on pause. So let's turn our attention to calorimetry. So this is an important diagram because it helps keep track. This is what typically happens with a solid when we add energy to it. Imagine putting a Bunsen burner under it. And the first thing that happens is in A, the temperature's rising steadily as we add energy. And then we get to the melting point, and we got to pay for the melting. When I was a kid, I used to think that once you started melting, it all inevitably melted because it was like a contagion, you know. And it's not like that. You can actually stop melting just by stop heating. It's like you can half melt something, have it half liquid, half solid, and it just stays like that until you put more energy in. So in B, we've got the melting process. There's no temperature change. It's just all the energy is used for the melting until it's all melted. Because you're breaking bonds. You're just changing the bonding structure. And then as you put more energy in, you start rising the temperature. It does not rise at the same rate as it did in A. So maybe a solid needs relatively little energy to change its temperature, but the same substance as a liquid will need a lot of energy to change its temperature. It's just the way it goes. You can't predict it easily. You've got to look it up in a book. So we have this region C where we're raising the temperature of a liquid until we get to the point where it's all at its melting point, at its boiling point, and then we have a plateau where we're just putting energy in to cause vaporization. And then when it's all vaporized, then we can go to E where we increase the temperature of the vapor particles. Now that means they go faster, you know. So visually, when we're increasing the temperature of the solid, they're vibrating more. When we're increasing the temperature of the liquid, they're going faster but still hitting each other. And when we increase the temperature of the vapor, they're going faster and mainly hitting the walls of the container. That's the kind of thing that changes. If there's any exaggeration in that diagram, it's that the plateaus are much wider than I've drawn them. They're too narrow as it stands. So if you want to store energy, the better way to store energy is to change its phase. Change it from a solid to a liquid, and that will store a ton of energy, because if you can then change it back into a solid, you get all the energy back. Go from a liquid to a vapor. Takes a lot of energy, but if you can liquefy it, you get all the energy back, and that's the principle behind AC. You can't particularly store much energy in heating something up, although, you know, as a little boy living in England where there was no central heating, everything was done by fires in rooms. The bedrooms in the wintertime would get like incredibly cold. And you'd make a hot water bottle. You get this little bottle and you'd fill it with boiling hot water, and you'd take it upstairs and put it into the bed, and if you were lucky you'd put it in a few minutes early so that it would like dry the bed out, and if you weren't so lucky you got shoved in with this water bottle, it would burn your feet, but your chest would be frozen, you know, damp and cold, and then bit by bit the bed would warm up and then you'd fall asleep. Then in the morning you'd wake up and your feet would be on this like pretty kind of like coolish, still warm but not that warm hot water bottle, and you'd get up and get dressed and you'd go to work kind of thing. Why not change phases in that case? Well, it contains enough energy. This little water bottle contains enough energy, and it's easy to do. You just pour hot water in, you know. But if you really want to do this on an industrial scale, you're much better off changing phase than you are changing temperature. So we're going to play a game which is basically, how do I characterize the relationship between the temperature change and the energy that's put in? You know, some things heat up quickly, some things heat up slowly. Yeah. Some things heat up with a little bit of energy, some things need a lot of energy to change their temperature. How do I characterize that? I use a thing called the specific heat. So, I need to come down here and get a pen. Oh, you're going to give me a hard time again? Sorry. Let's try that again. Yeah, there we go. Okay. So these things here are, it's one of those days, sorry. My pen is there, but you're refusing to write. Okay. Just take you out, let you reset yourself, bring you back. Now, let's try turning you out of that mode, and let's try turning you back into that mode. Yeah, there we go. So that depends on specific heat, that depends on specific heat, and that depends on specific heat. So I could have the specific heat for the solid, specific heat for the liquid, specific heat for the vapor. And this bit depends upon, that bit depends upon the latent heat, and that bit depends upon the latent heat. So the names are not literal, specific meaning and latent, they're just names. You look those up in a book, or I give you them. Heat capacity. If I have an object, Heat capacity is the amount of energy needed to raise the temperature of this sample by 1 degree. So I could have a joules per degree Kelvin, a joules per degree C, or a calories per degree C. You'll see them all kicking around. And it's basically the specific heat is equal to, I'd really say, the heat divided by the temperature change. How much heat you need to put in divided by the temperature change. We don't actually, we tend to talk more in terms of specific heat. And the specific heat is for the material. This is for a sample. And this is for a material. And for the like the difference between mass and density. Yeah? Density is for the material, mass is for a sample of that material. Specific capacity is the amount of energy needed to raise the unit mass of the substance by 1 degree. So now it's like, well, joules per kilogram K, or joules per kilogram degree C, or you could have calories per gram degree C. It's like, we use this one or this one. They're both the same number, because a degree C is like 1 Kelvin. It's like the same thing. What is the specific heat capacity of a solid gold if it takes, so here we have solid gold, and it takes 3096 joules to raise the temperature. That's my Q. To raise the temperature, my delta T is equal to 6 degrees C, and my M is equal to 4 kilograms. So I say, well, my specific heat, little c, is equal to Q over M delta T, which equals 3096 over 6 times 4, which equals somewhere 3096 divided by 6 fours are 24. So that's going to be 129, and will be joules per kilogram degree C. So it's simple as that. Not much, actually, in the scheme of things, not much. It's a relatively small number. That means it doesn't take much heat to change its temperature. Heats up relatively easily, which is why we like it. We like it in jewelry, because if you put something on that took a long time to get to body temperature, it would feel cold on you until it got to body temperature. But you put a metal necklace on or something like that, and it very quickly gets to temperature. Consider putting a 1 kilogram sample of high specific heat material and a 1 kilogram sample of a low specific heat material. Let's make this specific. Let's make this concrete. Sorry. We're going to use concrete, and we're going to use aluminum. They're an aluminum block and a concrete block. And we put them in an oven. And they both start off at room temperature, because that's what we took them for. And we're going to say what happens to them as they're in the oven. Which material will heat up fastest? It's going to be the... so this is aluminum, and this is concrete. And this is the high specific heat, high C. And this is the low C. Yep. So your gut feeling, I think, tells you the aluminum is going to heat up quicker, yes? Yeah. Concrete is kind of slow to react. So which will heat up fastest? Aluminum, which means the low specific heat material heats up fast. Doesn't take much energy to change its temperature. Yeah. Which material requires more heat to reach its final temperature? If you need a lot of heat to get a temperature change, you're going to need a lot of heat to reach your final temperature. So it's going to be the concrete will take a lot more heat to get to that temperature. So that would mean the high specific heat material. Takes a lot of heat to change temperature. There's a lot of temperature to change. That means a lot of energy. and which will store more energy because of its temperature change? Oh, well, if it took a lot of energy to change its temperature, that energy is inside the object. It's not wasted, it's inside the object. So which stores more energy? The high specific heat material. And I think it's worth just stopping for a minute and just thinking about this, because they both have their uses. If I want to make a cooking utensil, I want my pan to get to temperature quickly. I don't want to have to waste a lot of energy warming the pan up when I want to warm the food up. So I'm going to make my cooking utensil out of a metal like aluminum rather than a ceramic like concrete. You know. Now they do put thin layers of ceramic sometimes on cooking utensils so they're easier to clean, but that's a thin layer. You know? On the same understanding, if I made my house out of aluminum, it would be oppressive, because any energy that came in would immediately well, not immediately, but would be easily changed into temperature change. So the sun shines on it and I get temperature change, I get hot. And it's got a high temperature, which makes me feel uncomfortable. And then at night, that energy immediately goes away, and now I've got a cold house. Whereas if I make the same house out of brick or out of stone, when the sun shines on it, it takes a long time to heat up. So the temperature stays pretty constant. All this energy has been absorbed. And then the nice thing is at night, when the sun goes down, the energy is still in the walls. And it takes a long time for that energy to bleed away. So the temperature again stays stable. So high specific heat materials tend to give you thermal stability. It takes a lot to make them hotter, it takes a lot to make them colder. Whereas low specific heat materials give you reactivity. So they both have their uses. It's not that one's good and one's bad. They both have their uses. And so on here, let's just close this loop a bit. So on this diagram, a high specific heat material would be a big temperature range, big temperature change. So a high specific heat material would be like that. And a low specific heat material would be like that. So in this diagram, that's probably the highest specific heat, and that's probably the lowest specific heat. So you can recognize it from the slope. What about changing from solid to liquid or from liquid to vapor? For that we use this latent heat, and there's two versions of this, but they both refer to the material. And one is the latent heat between solid and liquid, and it's got various names, but the most common name is latent heat of crystallization, even if it's not going to become a crystal. And to go from liquid to vapor, we have latent heat of vaporization. Now that doesn't mean to say it has to vaporize. When you're condensing a gas, when you're condensing a vapor into a liquid, it's the same number. Either way, just they have to give it a name. So don't think it's only when you vaporize, and if you go from the vapor to the liquid, this doesn't work anymore. It's the same number. It's just they had to call it something. And this is simply how much energy you need for how much mass you've got. It's joules per kilogram. That's the value. What's the latent heat of crystallization of gold if it takes? So Q is equal to 20100 joules, and the M is equal to 0.3 kilograms. And I say, well, let's have a look. My L is equal to Q over M, which equals 20100 over 0.3, which equals, can I do this? Let's just do it. 20100 divided by 0.3 is equal to 67000, and it will be joules per kilogram. So simple as that. Now let's do some calorimetry. The whole basis of calorimetry is I kind of put two things in a container and I let them sort themselves out. I go for equilibrium. So I put a hot thing with a cold thing, and the hot thing gives energy to the cold thing, and we go to a final temperature. When they have the same temperature, they are in thermal equilibrium. Remember that from the zeroth law? When you have this, when you're in thermal contact, but there's no heat exchanged, you're in thermal equilibrium, and you're in thermal equilibrium when you're at the same temperature. And there's various examples for this. The simplest one is something that's not going to change its phase. So brass that's hot put into a liquid that's cool, or brass that's cold put into a liquid that's hot. The brass doesn't change, not under the typical values. Brass doesn't melt, brass doesn't vaporize under what the circumstances. Then the next level of difficulty is you put in things that will change phase. So you might have an ice cube in with water, and the ice cube will melt and become water. Got to take that into account. Then the third level of difficulty is you put in things that will change phase that aren't the same. So you might have butter in water. So you have solid butter, which then heats up, which then melts, which becomes then liquid butter, which heats up, but it never becomes water. So there's the three levels of complexity that we deal with, and we just learn how to do them. So in an isolated system, the heat lost by one element equals the heat gained by the other element, and so consider a hot solid to a cold liquid and see what happens. So here's an example. So 4 kilogram (20°C) sphere with a specific heat for this material of 8 joules per kilogram degree C is dropped into a calorimeter, a bucket, that contains 6 kilograms of 10°C fluid, and the specific for the fluid is equal to 4 joules per kilogram degree C. What's the final temperature? TF. When you put them together, what's the final temperature? I think it's worthwhile to remember this diagram. Now, what we're doing is we're taking this solid and we're basically going to, it's got high temperature, it's going to just decrease in temperature. So we're just going to be working like here. And for the liquid, it's going to just get warmer. So the liquid is in this liquid phase, it's going to be there. We don't have to worry about changes of phase. It's the simplest one. Later on, we'll get changes in phase and we'll have to take them into account. The way I do these is I say Q lost plus Q gained equals 0. I used to put Q lost equals Q gained, but you've got to mess with your temperatures then. So I find this a bit easier now. Let's get this over the way. I'm going to say, well, let's have a look. It's going to be the mass of the, it doesn't matter which way around it is, the mass of the sphere times the specific heat for the sphere times the temperature change for the sphere plus the mass of the liquid times specific heat of the liquid times the temperature change for the liquid equals 0. If you add together what was lost with what was gained, you get 0. So the mass of the sphere is 4, and the specific heat of the sphere is 8. And the temperature change for the sphere, I don't know. But with temperature changes, like all changes, we tend to do T final minus T initial. So let's just call it T final minus, and the T initial was 20. Now T final will be less than 20. So that's going to be a negative bit. That's all right. It is a negative bit. It's Q lost. Then we add on to that the mass of the liquid, which is 6, plus the specific heat of the liquid, which is 4, times the temperature change for the liquid, which is T final minus, and we're going to have our initial temperature, which is 10. Now the final temperature is going to be higher than 10, so that bit's going to be a positive bit, and that's how they two cancel each other out. The way that I was originally taught was you said heat lost equaled heat gained, and you had to play a game with the temperatures, so you always ended up with a positive number. And that's like, why do that? Why not just write it down this way, T final minus T initial, and it kind of works out nicely. 3 8s are 24, 4 8s are 32, that's 32 TF minus 32, 64, 640, is that right? 32 times 2 would be 64, times 20 would be 640, plus 24 TF minus 240 equals 0. So I can say 56 TF minus, they're both minuses, let's have a look, that's going to be 880, thank you, equals 0, so TF is equal to 880 over 56, which equals 15.7. So, there we have it. Just checking my time. Took the time. So not bad, you just put them in. Yeah. This next one, a little bit more complicated. And that's because of this. We're going to take, there's my solid water, which is ice. And there's my melting. And here's my liquid water. And I'm going to take cold ice. It's lower than its melting point. And I'm going to heat it up to its melting point. I'm going to melt it. And I'm going to have a bit of energy left over, so it's going to heat up somewhat. And there's my T final. And that's all going to be paid for by the cooling T hot. So this hot water is going to cool, and that Q is going to pay for these changes. If I have more hot water, I'll get if I get more hot water, I'll get a higher final temperature than initially. So. But it's important, I think it's important, because what you see here is you have 1 term, 2 terms, 3 terms, 4 terms. There's 4 bits to this calculation. I say Q gained plus Q lost equals 0. But now there's 4 bits to this. Let's draw a diagram of it. So we have 4 kilograms minus 10 degrees C is dropped into a calorimeter that contains 8 kilograms of 20 degrees C water. Now we're given some other stuff. For ice, sea ice is equal to 2 joules per kilogram degree C, and sea water is equal to 5 joules per kilogram degree C, and the latent heat, oh man, latent heat for crystallization is equal to 6 joules per kilogram, and your latent heat for vaporization, you're not going to get close to that, is equal to 14 joules per kilogram. So I'm throwing a bit more information at you. We work through these just one at a time, and we say, well, I have the mass of the ice times specific heat for ice times the temperature change for the ice. That's just getting that piece of ice to its melting point. And then we're going to have the mass of the ice times the latent heat for crystallization. That's to melt it. Plus, now, it's not ice anymore, it's water, but it's still the mass of the ice. If you like, you can put ice water, but it's still the mass of the ice, times the specific heat for water, times the temperature change for my ice water. Let's call it ice water. So those are those first three, added to the mass of the hot water times specific heat for water times the temperature change for the hot water equals 0. So it's that bit plus that bit plus that bit plus that bit. And three of them are going to be positive and one of them is going to be negative, and it's going to work out. Mass of the ice is 4. Specific heat for ice is 2. Temperature change. I know this temperature change because I know ice melts at 0 degrees C. So it would be my final temperature, which is 0, minus my initial temperature, which is minus 10. So I have the mass of the ice, the specific heat for the ice, and then I have the final temperature of the ice. It doesn't go above 0 degrees. Minus the initial temperature of the ice, and it's minus 10. So there's a negative there. Okay, I can deal with that. I'm going to do it vertically because I get a bit more space out if I do it that way. Added to the mass of the ice, which is 4, times the latent heat of crystallization, which is 6. That's that second one done. And then I have the mass of the ice. Well, it's water, so it's mass of the ice, water. But now it is water, of course. So I want 5 for my specific heat times my final temperature minus, well, initially it was ice, so 0. So this is that ice, which is now in here and is melted. So it's the mass of that amount of stuff, which is 4 kilograms, but now it's water. And its temperature changed, well, when it first became water, it was 0 degrees. And it's going to go to your equilibrium bit. That's 3 of them done. And now the fourth one done is the mass of the water times the temperature change, times the specific heat for water, which is 5, because it's still water, times T final minus T hot. And T hot was 20. So those equals 0. So that would be 4 times 2 is 8. So it would be 8 times 0 is 0. Minus 8 times 10 is 80. Added to 24. Added to 20 TF minus nothing, because 20 times nothing is nothing, added to 40 TF minus 40 times 20 is 800 equals 0. So now let's have a look. I have 80 plus 24 plus 20 TF plus 4 TF. Let me just check on that, is that right? 40 TF, thank you. Sounded a bit odd. Minus 800 equals 0. So that's going to be 20 and 40 makes 60 TF. Now, I got 80 and 24 making 104 plus 104 minus 800. So 60 TF, 60 TF is equal to 800 minus 104 is 696. So TF is equal to 696 over 60. TF is equal to 116. And 6 is into that 11.6 degrees C. And that's what I was supposed to get.